I'm super excited actually to be here and to share with you some of the preliminary work that we're doing, and this is still kind of fresh, hot off the presses, in terms of mapping skill sets, and so at TapRecruit, and some of the ways that we're using different types of embeddings. So I'm a research scientist. We do a lot in my research science group. We sort of have two different roles, one of which is sort of kicking the tires on new technologies and new ways of doing things. And so actually a lot of this talk is going to be focused on some of that work that we've done trialing through different types of embeddings models and dealing with issues to do with natural language processing and corpus generation in that process. And the other part of what I do is actually do primary research, which actually fuels some of our product, but also I think there's a lot about Travis's keynote that sort of really hit home for me in terms of, when you find something really interesting that you think that the community should definitely have, is making that very publicly available. And so this is part of an ongoing sort of effort. What I'm going to be presenting to you is still very preliminary. It's only in the pilot results side of it, of this sort of skill mapping. And I think that's really important, just as an example set for this type of analysis and showing you a little bit about different types of embeddings. But I think it's also really interesting from a personal career standpoint, things about, which technologies should we be investing in, and how we think about writing job descriptions is very important to that process. So, I should have pushed this up. The link to where the slides are, this PDF, and I will update that as we go along, is here. If you take a QC, this should take you straight to the link, and I'll show this at the end as well. So, we are a New York-based startup, and we basically design software around recruiting. And so we've been actually running a job search site for about 3-4 years now. And so we have this amazing corpus of job description data that is actually going to be the basis of a lot of my talk. And so we use that to give you a bit of background about why, I find it such an interest, why NLP is so important to our work. We use that to power a smart editor that I'm going to just show you quickly, that tells you how to write better job descriptions. And we go beyond what some people do in terms of just language, in terms of how language impacts bias, but really understand what's the basis of a job, what are the skills that are really important. And combined with something like, I think, 3 million salaries, we understand the job, we break down the requirements and try and estimate salaries. And we also try and give companies increasingly ideas about, if you put this job description up, how many candidates are you likely to get? What is your chance of actually hiring for that? So we're trying to do pipeline health monitoring. But what's central to all of these is actually taking a corpus and breaking it down into the actual skills. And so this is sort of what our editor looks like. You can see that, I don't know if this is going to come up. You can see that we have a lot of sort of language that goes into this. There are suggestions, and there's a lot of stuff in terms of the different types of, as in this, on one hand it's language, on the other side it's about talking about the skills. And you can see that, for example, the number of applications and things like that, we sort of track on that. So language matters a lot in job descriptions, and so you can see that a lot of conventional job description matching algorithms, and I'm sure many of you are receiving suggestions based on those, will take your job title and find you something else that has the same job title, because that might seem like a reasonable thing to do. This is a really problematic process, because you can take the same job title, and actually, Kraft Foods shouldn't be the same in both of them, jobs can have the same title, but they can vary dramatically in terms of the required experience. And you'll see this when if you're a finance manager, you'll be getting both of these types of jobs. In terms of the required education, one is quite a junior job in a certain type of company, and the other is quite a senior job in another type of company. And what I think we've been able to do is break it down into, you can have different titles, but these are essentially two very similar jobs, and they're also described in quite different ways. So I've highlighted some of the ways in which language, for example, consulting experience can be described. Data analysis tools, especially SQL, can be described quite differently. And we can show you that as in breaking it down and actually understanding what's at the heart of this is really critical. So the question that I wanted to talk about today is how have data science skills changed over time? And this time point, we're talking about the last 3 years, and how much have we seen change? And so I'm going to go through some of the approaches that we considered in answering this question and some of the pros and cons of that in the context of natural language processing. And this is going to be very non-mathematical because I stopped doing math when I was 18 years old. And so this is going to be very practitioner focused and the sort of packages that we've dealt with and the pre-processing issues that we've dealt with. That's not to say I don't enjoy doing math, but if you all went to Leland's talk, I think that has got you over the point of where I need you to be. Probably you could give this talk better than I can. So how do we answer this question, and what are two conventional ways of answering this question? First is manual feature extraction. So, this is regex or other forms of tokenization and pre-processing into a number of tags, for example. This is, at its heart, a very opinionated process because you're only going to create features that you are looking for. And so it is somewhat, I would call it supervised, but that's a very bad term to use when you're in a room with machine learning people as well. But it is sort of curated, right? And so it's artisanal, it's by hand, and you already know what you're looking for. The other sort of end of things is things like dynamic topic modeling, which are a little less, so basically you break down documents into bags of words, and you don't care about what order they come in. It's a matter of how much do these words co-occur over time and how important are they in the process of things. And what you can see here, and David, so the person who's our own personal hero at TapRecruit sort of was one of the first people that came up with this dynamic topic modeling. And you can see some examples of, I think these were science articles from the magazine Science on physics or atomic physics. And essentially you see from, across time, we've seen changes in the words. And what they were able to show is that with a lot of curation, like, in the 1800s to the 1900s, in the 1880s to 1900, there's a lot of talk about matter, and then electrons pick up, and then quantum picks up. I can't really personally figure that out as a non-atomic physicist from the set of 10 words that they show here. So that involves actually a lot of looking into those, the things that are coming up lower along the list and trying to really parse that out, or again, being kind of opinionated and being like, these things cluster together, and so this is an example of a quantum dynamic sort of, like as in this is a topic that comes from that. So both of these approaches, I think, have done us very well. They are kind of manual. They're not very easy to find new things. Dynamic topic modeling is a little bit better at that process, but they do involve quite a lot of loss of context, and like as in there are companies, for example, especially in job descriptions, and you guys are probably well aware, when you search for Python, someone will describe their stack as Python, but it's a finance role, right? So you're like, okay, well, that didn't really help me. These are problems that you can have when you're using these sorts of approaches. So the model that I'm sure you're all aware of by now are things that are word embeddings, which are essentially low-dimensional transformations of unsupervised sort of text clustering, which is my really not very accurate way of describing it, but that's what it represents to me. And essentially, what we do is we iterate through these you guys know corpuses, and we take words and we extract, and the whole basic intuition behind word embeddings is that a word is judged by the neighbors it keeps. And so if we were interested in a word like Python, and these are some examples to understand what would happen, we take their context, and this is just dimensionality reduction. So usually these are in 100, 200, 300 dimensions, but now I'm just going to map it into 2 dimensions just for the sake of ease. And we get a sense of, okay, so object-oriented, Java, C++, programming language, that's great from these sets of words. And say we have another corpus, again, this is our job description corpus, and we have more languages, right? Language gets moved around a little bit, and all of these sort of get refined a little bit more as we add more and more things to it. One of the big problems with word embeddings is that every token is represented by a single sort of in one way. So even though language in the context of programming means something, and it sort of doesn't actually have two meanings, but it's going to get moved to the mean of those two distances, right? So say you had a lot more language, you had a lot more translation documents, language would get moved in that direction. So it does depend on the representation of some of those, of the documents in your corpus, and that's something important to remember. One of the beauties of embeddings is that in a totally unsupervised way, they can capture entity relationships, and I think this is just magic. I never stop being amazed by this. These are examples from the Stanford Glove project, which I think show this in amazing ways. So, you can see the difference between companies and their CEOs. And what I find really interesting is that the media companies sort of cluster away from sort of more traditional Fortune 500 companies. And that sort of relationship is actually maintained in those sorts of hierarchies. Comparatives and superlatives are also represented in these embeddings. And the last thing is in terms of, and I think this is probably best characterized example of it, this woman is to queen as man is to, for example, king. And so there's a lot of language and whatever assumptions of the corpus are very effectively captured. And that's both a pro and a con, right? I'm sure many of you have heard of the man is to computer programmer as woman is to housewife example. All of the biases of your corpus are also represented in the embeddings. So that's actually a perfect example of how you can use embeddings to do descriptive analysis. And really understand the basis of how we think about language, which is a very academic way of thinking about it. But if you're using these embeddings in contexts where they're actually going to matter, there are a whole range of debiasing tools, depending on the type of embedding and depending on the corpus, that might be important there. Because we all know that, or there's a Foucauldian notion that your language and your structure sort of represent power and impose power. So I'm actually going to talk about other types of embeddings, but I wanted to talk just a little bit about the processing pipeline and the pros and cons of using pre-trained embeddings, because I think a lot of people, if you're new to the space, that's a very important question. There's things that you don't necessarily keep in mind that we've struggled a little bit. So firstly, you have to generate a corpus, process that corpus, we generate a language model, and then we tune that language model, and we do a final application. This whole process on this left-hand side of a typical language model generation can take months. And so what's been amazing is when people have published these embedding models, they've actually allowed, have made freely available a lot of pre-trained word embeddings. And these word embeddings have been trained on different corpuses with different algorithms and with different types of vocabularies. And so this is actually very important for those of you who aren't as familiar with natural language processing. Say you want to use an embedding and you take, say, the Wikipedia corpus from Glove, but you want to do sentiment analysis. There's not a lot of sentiment in Wikipedia corpuses. And so you're not going to capture that in your outcome. It's not going to train very well. Versus Twitter. Twitter is I've heard cornucopia of malformed text and all sorts of insanity. It's great for a lot of things, and maybe that's something that's helpful in your, in trying to understand your Yelp reviews or your sentiment analysis. The Twitter embeddings are also really great, I've heard, for sort of adversarial training of text, because it's such a cornucopia of malformed text. But also, like as in the Common Crawl and Google News are also very useful methods. The one thing that I'd say is that the token size, you can see that the number of tokens, so the number of words, or depending on how they process them, varies. And you can see that the common crawl varies quite significantly. That's because there are two implementations of it, one of which is cased and the other which is uncased. And that's something I'm going to talk a little bit about later. The pre-processing steps that went into these embeddings are actually really important for you to consider and to go into the weeds of understanding because they're not very well documented. And so you need to make sure that if you're going to test them out on your text, that they do follow the same, because otherwise you're going to get a lot of unknowns and they're not going to relate to each other. So that's something that seems kind of obvious, but it's not something that you think of when you're like, okay, great, in 2 lines of GenSim text, I've got like this embedding working, and now I'm going to start applying it to my algorithm. The last thing is in terms of vector dimensionality, and that, again, Glove has done a great job in terms of allowing embeddings of different dimensionality become available, and they've trained them very well. And that also is in something to bear in mind is, do you need 300 dimensions and can you run that? So if you're doing stuff off, for example, mobile search, maybe you don't want a 300-dimensional model as part of your processing. Maybe a 25 will be fine, and it does also depend on the form of your corpus. The one thing that I haven't mentioned up here are things that are character-level embeddings. So these are all word-level embeddings. So fast text, for example, from Facebook is an example of a character-level embedding that's done pretty impressive things in some fields and not in others. And I think it has a lot of strength in those models. But it's in our case, in terms of corpuses and trying to understand semantic sort of relationships, I found it to be less effective. So your mileage may vary. So now we get into some of the problems with these pre-trained embeddings. And again, I sort of alluded to this earlier. This depends on your thing. In our case, these were actually really very important to us and for us to understand these processes. So in our particular case, we had a lot of issues with casing. It is very different to IT, and most of the embeddings that come out are uncased, and so they're all lowercase. So then it's trying to understand it, which happens very frequently in a lot of documents, versus IT, which is actually very important to us, like IT support and IT, is in skills. And so what happens is they both get resolved to a single vector, which is probably where the it is, and then it gets downsampled a lot, because that's how these word-to-vec deal with frequent words. There are a lot of issues with out-of-vocabulary words, especially when you're using pre-trained embeddings. So there are, in our case, we found that a lot of job description data was not found in any of the conventional embeddings. There's a lot of misspellings, for example. I can tell you that the most frequent word that we have in our job database is manager, which is not something you find in an embedding because people aren't normally talking about managers, they're talking about managers. So that's one of those other sorts of things. There's the other two sort of areas that are really important in terms of embedding models are polysemy, which are words that have multiple meanings, and multi-word expressions. And so front plus end means something very different to front end. And front end is spelled in a variety of different ways in job descriptions by people who don't have experience with front-end developers. And so there's no easy way to tokenize around that or to sort of merge them necessarily. And there are actually some, I didn't have time to show these, but there are some algorithmic ways that you can overcome these, except that the people who write the polysemy algorithms aren't the ones that write the ones for multi-word expressions, and so you're going to have to resolve them somehow yourself. So with all these problems, and in our use case, these were significant problems, they may not be in yours, and so that's something just to be aware of, is that we decided, okay, let's develop our own custom language models. And I want to just give a shout out to a couple of the different corpus processing models that I think are libraries that I think are amazing. We use Spacey a lot, but I've heard great things about the OpenNLP, and the core NLP has gotten a lot faster. And I think Google's Parsey McParsface is now part of the SyntaxNet group of parsers. And this is something that you have to consider, because you can go and regex the crap out of splitting tokens, but there is some semantic processing and there's lemmas and things like that, and dependency parsing that might be helpful to use more complicated systems. And we've actually the way that job language is written is so segmented. There's a lot of incomplete sentences. We basically had to write our own dependency parser because it doesn't work in the way that normal English works. And that's also going to be the case for a lot of things, like, Yelp reviews or other types of reviews. They're not normally written in normal English. So that's one thing. And then the second part of it is that's made this extraordinarily easy are these language modeling libraries. I'm a big fan of GenSim. The stuff that I'm going to be showing you today is built off TensorFlow. So I do a lot of the GenSim does a really good job of keeping up their embedding model to the latest and making sure that they're running on C and running really quickly. But those are the ones that I recommended. If you're doing distributed systems, I've heard amazing things about Amazon SageMaker. And I'm sure there are others, like you can basically go down. But this is today's one. I'm going to talk a bit more about TensorFlow. So the last thing that I would bear in mind with embeddings and training your own embeddings is there are a lot of hyperparameters to optimize, and what you optimize obviously depends on what your output is. And so if you optimize over a small window size, which is what I showed you the example of earlier, you essentially find things that are semantically similar. So what we're talking about are things that are substitutes. So, we might not in this room think that Python can be substituted by Java, but in the grand scheme of things, probably more so than Esperanto, right? And so those are the sorts of things. If we have a larger window size, we capture more semantic relatedness. And so these are more things like alternatives rather than substitutes in economic speak. And so these are domain level differences. So again, taking those previous examples, we see that SPSS is somehow now getting closer to Python and languages are further out. And so the window size is one way. Some of the algorithms show differences as well in terms of whether they capture semantic similarity versus relatedness. And that also depends on what your intention is. So, maybe you want alternatives. Maybe you just want to know that Python is part of the statistical model thing, and it's very distinct from, finance, for example, or FP&A roles. So this is just an example of, I think it's a TSNA of our custom embedding. So these were like the top 1,000 words, and that we did based on job description language. And generally, I found job description language, the other difficulty with it is that you have areas that are very, very unique to each job, and then you have areas that, and you guys know this, are very boilerplate. You have a lot of repetitive language, and so you put that into a topic modeling model, and you get all of the equal opportunities and perk statements because they are the most frequent things that come up in every single document, but that they are different enough that they might distinguish it. So I was actually really happy to see, and I'm going to show you these two examples, these two clusters here of language, equal opportunity language, and of, vision, like as in perks and benefits language. And we saw that, there's a lot more language that goes in there because this is a top, I think, 1,000 words. We're seeing things like medical and dental, which tend to be the most common, right? That makes sense. We also found, and this was actually surprising to me, was that what we call soft skills also cluster together, which is sort of interesting because soft skills are typically spread out throughout a job description. Like they're talked about in lots of different ways. They're not in their own segment, but clearly they happen enough with each other that they tend to sort of come together. And then the other thing is like experience. So all of the different ways we talk about experience also cluster together. And clearly my little corpus here has a lot of finance roles because there's quite a few examples of that in terms of the way that we talk about experience. So, I mean, I was pretty happy with this model, and then we use this. So I did talk about how at the start of the talk, I was mentioning how we want to know how they've changed over time. So it's great that I have this corpus, but what about the question of time? Yes?
What is the distance between these vectors that you use to say do a TSNE? Mm-hmm. What was that distance? So once you encode your words, the corpus in the vectors of numbers, mm-hmm. somehow you have to specify the distance between 2 points to determine what's close and what's not.
Yes, so each of the words have like a 300-dimension vector, and then it basically does a vector reduction. I didn't encode the TSNE. I just use TensorFlow's like output of that process to collapse them into a couple of dimensions. So it takes the 300 dimensions and...
But in 300 dimensions, the distance between points, is it Euclidean or is similarity measure or?
Oh, sorry, it's the distance. So the distance is it is a similarity dimension. So the closer they are, the more similar they are. The further they are, the more dissimilar they are. Yeah. And so that's based on the window size as well. So like if they occur within a window size, it's like a 1 versus if it doesn't occur within the window size, it's 0, and then it goes through many levels of extrapolation. So I mentioned here that sorry, I didn't explain that super well, but we have a whole bunch of dimensions, but we haven't looked at time. And there are a couple of different ways of doing this. And this is actually, maybe not everyone's interested in time as a dimension, but you can substitute, in your case, time as any other category that you use, right? So in this case, I'm showing you time. I'm not allowed to show you seniority because that goes into our product development. But you can imagine that that's one of the ways that we would consider it. And so there's a couple of different ways that people have come up with dealing with dynamic embeddings. And one of which is just training lots of different embeddings and then hand stitching them together. So through time. And the other alternative is training them all together. And so this is a newer technique, and actually that's what I'm going to be using in today's, the results that I'll show you. So first thing is in terms of data, static embeddings are really data hungry. So you're basically training a whole embedding. So I showed you before that each embedding that's been pre-trained is like millions of words and millions of tokens, right? So you need to have a really high quality embedding for each of the time slices. And people have done this analysis over, like you might think, okay, well, you have 3 time slices, how bad can that be? But people are doing this over like 100 time slices. And so that becomes it becomes quite significant. So these 2 papers, for example, needed billions of words. So they had to use the Google Books corpus because it just wasn't enough words to make that work. And then the other thing is that they require stitching because the dimensions aren't comparable across slices. You're going to have words in some of those slices that aren't represented in other slices, especially if you're doing it year by year. And so how do you compute, like, when words drop out? And one of the things with these embeddings is that you actually have to restrict your vocabulary. You do have to restrict your vocabulary a little bit in order to get, to be effective, and so there will be dropout. On the other hand, dynamic embeddings are pretty efficient. So we have done this with maybe 1 million words over 3 years. Because I've been trying to push the boundaries of so 1 million words over 3 years, so 300,000 words per year. And we've been trying to push the thing of how low can you go. I think the Balmer and Mant article has done it with tweets, like 300,000 tweets over 6 years or something. So it's like egregiously low, and they were all news tweets. So, but I found that in general, you don't want to go too high, but you also don't want to go too low. So it's a little bit of a Goldilocks thing. But it's one of those things that we've just been trying to see how low we can go. So I think we did it with 1.5 million words, and that actually worked very well over 3 years. So 500,000 words per year. The other thing that's beautiful about this is it doesn't require stitching it in alignment. So even if a word doesn't happen in every single time span, there is a probabilistic function that links it between the time spans. And I'll talk a little bit about that. That's exactly what the exponential family stuff that I sort of alluded to in the start of my talk, the title of my talk means. So, first thing, any MBAs in the house? Oh dear. You finished, right? Yeah? Okay, awesome. Because the demand for MBAs is one of the things that came out of our analysis. So the beauty of the embeddings model that we tested, what it does is it gives you out, the top words that come out of it, and we went back to our databases and took a look. And MBAs actually, the demand for MBAs in job descriptions has fallen about 40%, which is reasonably significant. Not something you want to hear if you're $50,000 in the way of MBA school. And I'm sure we have a lot of PhDs in the house. I'm not going to ask you to stick your hands up. I put in PhD. PhD didn't come out of our analysis. I put it in because I was kind of curious, okay, well, if MBAs are dropping, how are PhDs doing? And what we're seeing is actually it is dropping a little bit in all jobs, but not as significantly as MBA. And so actually what I was surprised about is in data science jobs, then there's like a 40% reduction in the requirements for PhDs in those roles, which I thought was very strange. So I went back and actually did a bit of analysis of looking at like, okay, so like, are we getting more, do we want more people with machine learning backgrounds or whatever else? And actually in all of those areas, there's been a shift, and we're not actually seeing more machine learning required in the data science roles. So it's sort of interesting that the PhD is getting less valuable, which is great for everyone else who hasn't spent 7 years of their life doing one or intending to do one. Yes?
Is it, one reason could be just a lot of the rebranding of job titles, or like,
So,
like say a lot of the, even nowadays, even like previous like risk analysts or different type of analysts, or like the titles are rebranded into.
we counted them as well. So they're part of actually the group that I counted in the original to begin with. So everything that, so I've used in my data science jobs, it's not only data scientists, but it's biz intelligence people, data engineers. We counted the whole swath of anyone who touches data in any meaningful way. And so actually, I think that's actually even more interesting. So if you're thinking about like, as in from 5 years ago, when you're looking at biz analysts and BI people, like that's been the big boon. Yes.
So maybe you're going to talk about this, but how did you get to this? How did you get from the word embeddings that you trained to like being able to say this sort of?
So we pulled out, so I don't get to this because I was trying to talk about just the results. But so the embeddings actually gave us, so the dynamic embedding, the output of that process is a list of words, essentially tokens that came out of that process that will show the most change. And then it's incumbent on you to go back and start looking through where you're seeing the change. And so there are time slices. So it actually, with each of those, you get a different model. So I had 3 time slices. I have 3 different models that I put into the TensorFlow projector board and just tracked how they moved around in that process. So you kind of, it tells you big picture, and then you have to go and figure out the small picture side of things. So the other sort of shifts that we're seeing actually, and this is very interesting, it was completely opposite of what I thought. Tableau and Power BI came out of our analysis as significant shifters. Now Tableau doesn't look so big because Power BI is doing amazing things, so well done Microsoft, I guess, our sponsors. But Power BI is seeing quite dramatic increases. So is Tableau, actually. So data viz skills are actually picking up in a way. And that was opposite of what I thought. I thought, okay, well, machine learning and deep learning are becoming so hot and everything else, but yes, that's happening in startups, but it's not happening across the board in every single role. And actually the biggest strength and the biggest growth in data science skills that we're seeing are in like a lot of Fortune 500 companies that are sort of building out their marketing and sales teams and trying to make them a lot more data driven. Hadoop came out of our analysis as one of the biggest changes. And my CTO and I disagreed because I'm like, I hear about Hadoop at all these conferences, but it makes sense given AWS is kind of eating. I hope there's no Hadoop people here, but AWS is making it a lot easier, and so Hadoop is becoming less of a requirement. I threw in Spark as an example just to see, how is that doing, because we expected all of the stuff with ML to go up, and Spark is staying pretty stable actually. It's Hadoop that's sort of going down. The changes in Spark aren't significant. And our favorite, so Perl came out of the analysis, and Perl is, I love Perl as an linguist. It's amazing. It did a lot of great things for us. But that's one of the areas where it's going down, and Python is sort of eating that lunch. The one thing that my CTO didn't want me to come and tell you about is that in data analyst roles, scientist roles, we're seeing actually we're seeing an increase in Java, surprisingly. So it's not on the slide. I'm letting you know. Make sure your job descriptions are effectively written as PyData people. But I think that's partly because this role is becoming, we're seeing an increase in scripting languages coming to the fore in these processes. And so people ask for Python, Java, or C++, even if they're very happy with Python. So that might be, it's a small gain, but it's been interesting, especially because I think there was some recent stuff with Stack Overflow or someone, maybe it was Indeed, that was talking about like Java, like doing very, very well in job listings. So the last part of my talk is talking about the exponential family embedding. So I kept you all here till the end to talk about, to sort of tell you a little bit about how this sort of embedding structure fits in the broader scheme of things. So just as regression is to generalize linear models, Word2Vec is to this family embeddings, the exponential family embeddings. And essentially what these guys do, the intuition behind this is that probabilistic, adding some intuition about what type of data you have, so following Leyland's talk, allows you to get embeddings of different sort of data types. And I think that's actually fascinating. So what I showed you today was with language modeling, it's essentially a form of Bernoulli embedding. So it's binary data of whether a word exists or not in that context. And so here, there's a nod to my whole Java thing. If the data point is Java, we have context around proficiency programming and Python and things like that. We also have the ability to attach for continuous data. For example, if you had edges and nodes, right? So if you had weighted graphs, to attach a Gaussian embedding to this. So, if you had the number of flights that were going out of different airports, for example, or whatever is your sort of graph-based model, you can attach a Gaussian embedding. So using that knowledge, you can create embeddings out of graphs too. And the last sort of method is in terms of Poisson embedding. And I found this one to be the most exciting, to be honest, because you can just take your categorical data, and we have a lot of categorical data, and create embeddings out of it. And actually, that's something that I'm going to be working on next, is to try and understand how we can do connections between embeddings based on categorical categories. So one of the beauties of this is, and the way that this is used is in actually economics sort of market understandings, and I'm going to massacre that as a way of describing it, is to understand what people buy together and what people don't buy together. And so this is something I think is really helpful, because we can actually go in and use that to sort of predict whether you'll want to go to James Powell's talk based on, is he in here? No, he's not, good. But based on the fact that he doesn't even have a title in his talk, right? So we can be like, okay, I really liked Emily's talk, I liked Angel's talk, I've got, the count and ordinal data is the number of stars I gave to those talks, and if based on that I like that, we can impute that based on no language. So again, these are ways that we can these could have just been numbers or categories, and we can actually sort of impute these, and these have actually been very effective in terms of, I think the group that did this work was really good with movie reviews, and they're really, they've been able to soup up recommendation systems based on these sorts of embeddings, because they're taking a person, an embedding of a person and an embedding of the different things that they've seen and sort of resolve them. So I think that's amazing. And again, this is just an example of, the way that these sorts of embeddings have been used to sort of figure out things that are similar. And again, using inner product combinations to figure out, okay, people typically buy chips with beer or chips with frozen pizza, but they don't buy Tide Pods with cinnamon toast necessarily, although they may not have at that point. Or that you won't buy two types of soup necessarily, like maybe that's enough soup. So, my question today was like, how have data science skills changed over time? I'm really happy to have shown you some preliminary results. What I've showed you today was the flavors of static word embeddings, and I wanted to highlight to you guys the importance of a corpus issue and the importance of pre-processing. Those are things that take up the most amount of time from an NLP standpoint, and the things that to keep in mind. And I know that they're not the most sexy thing to talk about, as the math is, but I think that that's actually really important. The things that I talk about were also considerations for developing custom embedding models, and the different types of dynamic models that we have, and the sort of things that you can do with these dynamic models. So time in this case was an example of the dynamic side of a Bernoulli embedding, but you can do a multivariate Bernoulli embedding and use categories, for example, as your multivariates. Or you can use other sorts of ordinal connections between them. And the last thing is in terms of that there are other members of these embeddings that actually do very good jobs in terms of recommendation systems without a lot of knowledge. And I think that's fascinating. I think they're awesome, and I would like for you all to start implementing them as soon as possible so I can see what your results look like. But with that, I wanted to thank you all. Hopefully I haven't gone over time because I cannot see what the time was. And if you guys want slides, if you want to contact me, I would be happy to discuss data science skills and other sorts of questions. Thank you.